Hi class, in this video we're going to prove the product rule, and part of the instructions is to actually use the formula that utilizes the functions as opposed to the alternative formula of u and v's. It ends up being the same, but it's easier to derive it in this format. And here's the basic idea. We have the product of two functions. As we differentiate, we're going to end up with the first function times the derivative of the second one, plus the derivative of the first function times the second function. And part of the problem is to actually define our function in terms of f and g's. And it's just easier to say, well, let it equal to p of x, and where p of x is the product of two functions. As we're stating that p of x is defined over the real numbers, meaning we don't have any divisions by 0. And that would be pretty much it. At this point, I'm going to be evaluating the actual function. So this is equivalent to the following. This is going to be the limit as h approaches 0. And we technically have the function with f and g's. So we're going to have f of x plus h, g of x plus h, and then minus the values of, actually let me rewrite it exactly as stated, f of x and the values of g of x, and then all over h. Now at the moment, the way that we have this expression, we're kind of stuck. Multiplying by conjugates is not going to work. It's not going to cancel anything on the top, where we end up with an expression like this. But part of the observations that can be done as we're differentiating functions is that a term cancels out. The term that cancels out, it's technically this term here. So what I'm going to do is I'm going to actually add a 0 and then replace it with that expression. And that's going to help us in the derivation of the formula. In other words, there's a term that cancels out that we don't get to see as the evaluation of the product of two functions. So in this case, let me rewrite it as this is equivalent to the limit as h approaches 0 of, and we still have the f of x plus h, g of x plus h. I'm just going to say that this is 0 minus the function f of x, g of x, and then technically over h. And I'm just putting the 0 there to justify that technically no value it's added. And I'm now going to substitute the 0 with this expression. So I'm going to be subtracting and adding. So technically we're not modifying the top at all. So at this point, we're looking at this is equivalent to the actual limit as h approaches 0 of f of x plus h, g of x plus h, and then I'm going to do the subtraction. So it's negative f of x plus h, g of x. So negative f of x plus h, technically g of x, and then plus f of x plus h, g of x, and then we have this being subtracted by the actual f of x, then the values of g of x. And then all of this happens to be still over h. Technically, there's a parenthesis here. Now, what I'm going to do is look for common factors and see if we're able to express the top in some sort of a format. And notice that we're looking for technically an f and a g prime. So for instance, from the top, we could factor on the first expression. I'm just going to factor the common factor of f of x plus h and technically f of x plus h. And we now have that this is equivalent to the actual limit as h approaches 0 of f of x plus h, and technically we're multiplying this quantity times g of x plus h minus g of x. And then from the second term, we're going to be factoring out, well, in this case, let's factor out the g. So we have plus, and in this case, this will be the values of g of x, and then times f of x plus h minus f of x, and then technically bracket here. And then we have all over the values of h. Now, what I'm going to do next here is technically unsimplify it and see technically this h as two fractions. So I'm going to express it as a fraction here and as a fraction with this term here. So I'm running out of space, so let me just move it to the next portion or the next page. And this is equivalent to the limit as h approaches 0 of, we still have the f of x plus h. And then I'm going to just express the numerator as g of x plus h minus g of x. And then I'm just going to put this over h. And then plus, so technically we still have that this is one chunk plus the values of g of x times f of x plus h minus f of x over the values of h. Now, at this point, I'm going to evaluate the limits, and I'm going to distribute the limit to technically the following terms. So I'm going to distribute it to the top, and I'm just going to separate it into two terms, and then also to the second function, which happens to be here, or the second fraction. So I'm going to rewrite the numerator as this is equivalent to the actual limit as h approaches 0 of f of x plus h times the actual limit as h approaches 0 of, this will be at g of x plus h minus g of x over the values of h plus, and technically this represents a constant since it doesn't have any h's. So this will just be g of x times the limit as h approaches 0 of technically f of x plus h minus f of x over the values of h. Now on the first term, let me just emphasize it here. As you apply the h, that just gets evaluated here. And we're left as a result from this term, just the value of f of x. And then I'm going to rewrite these limits and leave them exactly as they stand. So technically, we still have that's f of x times the actual limit as h approaches 0 of the quantity of g of x plus h minus g of x all over h, and then plus the values of g of x times just the limit as h approaches 0 of technically f of x plus h minus f of x divided by h. And then we technically need a disclaimer here. I'm just going to say on the disclaimer that technically note g prime of x is equal to the limit as h approaches 0 of g of x plus h minus g of x over h, and then f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So as a final note, I'm just going to rewrite it here. And in this case, it's our final p prime of x is equal to the actual limit as h approaches 0 of technically f of x. Actually, in this case, it's going to be p's. So p of x plus h minus p of x divided by h, and all of this simplified to this was equivalent. So let me write as p of x is equal to, and we have that this is just f of x times, this is going to be, well, g prime plus the values of g of x times, and this is going to be f prime of x. And this is just f prime of x. And at this point, we've actually proven this statement. So in other words, we rewrote the statement as f g prime, f prime, and g. And that's actually it.